Okay, today we're going to talk about exponential functions, differentiation, and integration. So some of this at the beginning is going to be review from pre-calculus. So if you didn't get it last year, this is your chance to make it up and make sure that you got it down carefully. Okay, so definition of the natural exponential function. The inverse function of the natural logarithmic function, f of x equals natural log of x, is called the natural exponential function and is denoted by f inverse of x is e to the x power. Okay, so e to the x and natural log of x are inverse of each other, just like multiplication and division. That is, if y equals e to the x power, if and only if x equals the natural log of y. Okay, so remember our statement that we had that logs are exponents? Well, right here, here's a log, this is the log, and hey, it's the exponent right there. So when you get confused, always remember that phrase, logs are exponents. The inverse relationship between the natural logarithmic function and the natural exponential function can be summarized as follows. So the natural log of e to the x is just x. So essentially what happens is the natural log and the e cancel out. And e to the natural log of x equals x. So again, those cancel out right there. Okay, then we solve some exponential equations. Okay, so I got a couple things I want to do here. I want to get rid of this e, and I want to get this exponent down off of that variable out of the exponent. So what I would do is I would natural log both sides of this equation. And if you remember your log rules, I can take my exponent down in front. So this is x plus 1 times natural log of e. But the natural log of e is just 1, so this cancels. And now I can just subtract 1 from both sides, and I get x equals the natural log of 7 minus 1. All right, which, if I need to know the decimal, I can figure out on my calculator. Whoops. The natural log of 7 minus 1. So that's approximately 0.9459. Okay, here I've got a natural log equation. I want to get rid of that natural log so I can solve for x. So what I would do is I would take e to that power on both sides, and then this cancels, and I get 2x minus 3 equals e to the 5th power. Now it's just algebra, right? Add 3. So 2x equals e to the 5th plus 3. And divide by 2. So x is e to the 5th plus 3 divided by 2, which is the exact answer. Or I can calculate that, e to the 5th plus 3, and divide that by 2. That comes out to about 75.707. So easy stuff, review from last year. Also review, so properties of exponential functions, e to the a times e to the b equals e to the a plus b. This should make complete sense. Okay, if I have, say, e to the 2nd times e to the 4th, well, remember, e to the 2nd is just e times e, and e to the 4th is just e times e times e times e, and if I'm multiplying those two things together, that's e to the 6th power, which is just e to the 2 plus 4 power. Okay, so this one here, e to the a divided by e to the b is e to the a minus b. It's just the opposite of this. So this would be something like e to the 7th over e to the 5th Well, remember that's E times E times E times E times E times E times E, 7 E's, over 5 E's. And then we just have a bunch of cancellations, which leaves 2 E's on top, which is E squared, which is E to the 7 minus 5 power. Okay, so you see how that works. So pretty easy stuff so far. Okay, properties of the natural exponential function. So the domain of f of x is e to the x is negative infinity to positive infinity. And the range is 0 to infinity. That's open-ended, of course. So this is what e to the x looks like. It's got a horizontal asymptote at 0. So it never really reaches 0, but it gets as close as you want. Okay, so I can put in any number I want in here and take e to that power. And I get out any number above 0. The function f of x equals e to the x is continuous, increasing, and 1-to-1 in its entire domain. The graph of f of x equals e to the x is concave upward, so you can see it curves, it gets steeper and steeper. Never quite gets vertical, though. The limit as x goes to negative infinity of e to the x is 0, so you can look at that here. If I go to negative infinity, this is going to have a horizontal asymptote, so its limit is 0. And the limit as x goes to positive infinity of e to the x is infinity, so this just is unbounded. It takes off and gets bigger and bigger and bigger. All right, derivatives. Now this is one that's easy to remember. The derivative of e to the x is e to the x. It's its own derivative. And the derivative of e to the u is e to the u times du dx. So that involves the chain rule there. So if you had something like e to the 2x and you wanted to take the derivative of that, okay, that'd be e to the 2x because the derivative of e to the x is e to the x, and then it would be chain rule, so I'd take the derivative of 2x would be 2, and I'd be done. Okay, find the derivative of each of the following. All right, so y prime is going to be e to the 2x minus 1 times the derivative of 2x minus 1, which is just 2. This one here, I would probably change this to be e to the negative 3x to the negative 1 power. Okay, so the derivative of that is going to be e to the negative 3x to the negative 1 power times the derivative of the inside. Okay, so the derivative of this. So that's going to be 3x to the negative 2. So if I was going to rewrite this and kind of clean this up a bit, this would be 3e to the negative 3 over x power over x squared. All right. Find the relative extrema of f of x equals x e to the x. Okay, so this is a product formula problem. So to find the relative extrema, we got to find the derivative and then set it equal to 0, right? So the derivative. So if f of x is x e to the x, then f prime of x is going to be 1 times e to the x plus x times the derivative of e to the x, which is just e to the x. All right, which I could rewrite as e to the x times 1 plus x. And then we want to set that equal to 0 to determine where the relative extrema are. Now, e to the x is never equal to 0, so I don't have to worry about this, but this is equal to 0, at x equals -1. So I have a relative extrema at -1. Okay, so now I can do the first derivative test on this thing, and since that's I can tell that that thing's going to be a minimum. Okay, so I'm going to have a minimum at x equals -1, and then y is going to be -1 e to the -1, which is going to be -1 over e. Okay. The standard normal probability density function. So show that the standard normal probability density function, f of x equals 1 over the square root of 2 pi times e to the negative x squared over 2 has inflection points when x is plus or minus 1. Okay, so if you remember, inflection points you have to find when the second derivative is 0. So this looks really scary. Keep in mind, this is just a constant right here. Okay, and taking a derivative of e to anything is not that difficult. So let's rewrite the problem here. Whoops, not x, pi. X would make it considerably more difficult. Okay, e to the negative x squared over 2. All right, so the first derivative of this thing is going to be 1 over the square root of 2 pi times e to the negative x squared over 2 times the derivative of this, which is going to be, let's see, this is really -1/2 x squared. Okay, so this is going to be negative x. Okay, so there's the first derivative. Let's double check and make sure that we got that right. Yes, we did. Okay, so now we're going to take the second derivative. Now this is a product rule this time. Okay, so we're going to just take this and kind of factor it out here in front. And we're going to product rule this. So this is going to be, if we take the derivative of this is -1 times e to the negative x squared over 2 plus negative x times the derivative of this, which is going to be e to the negative x squared over 2 times negative x. Okay, so then I can clean this thing up. Oops, I did that again. Why do I keep putting an x in here? This is a pi. Got it that time. Okay, so then let's see. This negative x times that negative x is going to be x squared. So this is going to be negative e to the negative x squared over 2 plus x squared e to the negative x squared over 2. And you know what? I could factor out the e to the negative x squared over 2. And that would leave me with -1 right here. So I'm going to put the -1 over here. And that would leave me with an x squared, which I can put in front. Okay. So then I'm going to go ahead and, so I got that correct. Now, when is that equal to 0? Well, again, this is never equal to 0 right here, so I don't have to worry about this. This can be factored into x minus 1, x plus 1. So this is going to be 0 at x is plus or minus 1. So I've got inflection points at plus or minus 1 along the x-axis. So if I wanted to know what those points actually were, I just take the 1 and the minus 1 and plug them back in the original equation, and that would tell me where the inflection points are. Okay, population of California. So the projected population in thousands, y is in thousands here, be really careful of that, of California from 2015 through 2030 can be modeled by y equals 34,696 times e to the 0.0097 t, where t represents the year and t equals 15 corresponds to 2015. At what rate will the population be changing in 2020? Okay, so since we want to know the change, we need to take the derivative of that thing. So y prime, well, that's going to be 34,696 e to the 0.0097 t times the derivative of this, which is 0.0097. Now I can multiply this by the 34,696. So y prime is going to be 336.5512 e to the 0.0097 t. Okay, so now I just have to plug in the 20. Okay, so I'm going to go ahead and plug 20 in right here. So and go ahead and calculate that. So times e to the 0.0097 times 20 power. So y prime comes out to be 408.606. That's in thousands. Okay, so I multiply that by 1,000. If I wanted to know the actual number, that'd be 408,606. Okay. Of course, that's going to be approximation, not going to be exact. All right, integration rules for exponential functions. So let u be a differentiable function of x. The integral of e to the x dx is e to the x plus c. And the integral of e to the u du is e to the u plus c. So find the indefinite integral, the integral of e to the 3x plus 1 dx. Okay, so here's what we're going to do. We've got a function inside a function here. So we're going to go ahead, let's go ahead and rewrite it first. We're going to go ahead and let u equal 3x plus 1, and then du is going to be 3dx. Okay, so I've got a dx. I don't have a 3, so I need a 1/3 to cancel this out. This is e to the u du. And the integral of e to the u du is just e to the u. So this is 1/3 e to the u plus c. And then we'll go ahead and put the 3x plus 1 back in for u. And there you go. Find the indefinite integral 5x e to the negative x squared power. Okay, so this is again another one we could use some u substitution on. All right, so let's rewrite it here a little bigger. 5x e to the negative x squared dx. Okay, so we're going to let u equal negative x squared, so that du is negative 2x dx. Okay. So then here's what we're going to write. We've got an e to the u. Du takes care of the x. Now I've got to get something in there to take care of the negative 2 being a 5. So I'm going to put a negative 5 halves in here. Okay? Because negative 2 times negative 5 halves is positive 5. Okay, so we should be pretty dialed in here. I can take the negative 5 halves outside here, which makes it super easy to integrate this thing. So this is going to be negative 5 halves times e to the u plus c. And then I'll go ahead and put negative x squared back in. And I'm done. Okay, find each indefinite integral. So e to the 1 over x divided by x squared dx. Okay, so here's what we're going to do. Let's take this and rewrite this a little bit, make it a little easier to work with. Let's make it the integral of e to the 1 over x times x to the negative 2 dx. Okay. So if we let u equal 1, let's see here. Let's change this too. We're going to make this x to the negative 1. Okay. So if we let u equal x to the negative 1, then du is negative 1 x to the negative 2 dx. All right, so I just have to deal with the negative here. So I can rewrite this equation as negative the integral e to the u du. Which is going to be negative e to the u. And I'll go ahead and plug the x to the negative 1 back in there. Oops, forgot my negative sign. Sorry, forgot what. Yeah, x to the negative 1 plus c, or negative u, or negative e 1 over x plus c. Okay, let's look at this one here. We've got the integral of sine e to the cosine dx, so we can let u equal cosine x, so that du is negative sine x dx. So now we can rewrite this as the negative, get rid of that negative, integral of e to the u du again. Which is just going to be negative e to the u plus c. And then we'll go ahead and plug in the, this is negative e to the cosine x plus c. All right. Evaluate each definite integral this time. Okay, so pretty much the same as before, except we know how to do definite integrals, right? So let's see, this one here. So the integral of e to the x is going to be e to the x times the derivative of that, which is going to be negative 1, evaluated from 0 to 1, which is going to be negative e to the negative 1 minus negative e to the 0 power. So those cancel, and I get negative 1 over e plus 1, which, I don't know, what's that approximately equal to? 0.632. Either one of those will do. This, of course, is exact, and that's approximate. Okay, this would be one we'd want to do by u substitution. So we will let u equal 1 plus e to the x, so that du is just e to the x dx. Now we can change this to be the integral of 1 over u du. Do I really want to change? I don't know if I really want to change these at this point. So the integral of 1 over u du is the natural log of the absolute value of u. So this becomes the natural log of the absolute value of u. And then I'm going to put back in the 1 plus e to the x, and we're evaluating that from 0 to 1 again. So this would equal the natural log of 1 plus e minus the natural log of 1 plus e to the 0, which is just 1. So this is positive. We don't need the absolute values. And I suppose you could write this as the natural log of 1 plus e over 2, like that, which comes out to be about 0.620. You can even leave it like this if you wanted to. Okay. Lastly, we've got the integral from negative 1 to 0 of e to the x cosine e to the x dx. So this is going to be a u substitution problem again. We will let u equal e to the x dx. I'm sorry, not dx, just e to the x. And then du is going to be e to the x dx. So this becomes the integral of cosine u du. Now I could plug these numbers into here and get, e to the 0 would be 1. and e to the negative 1 down here. But I think what I'm going to do, I'm going to probably wait and substitute that back in. So the integral, let's see, the integral of cosine is sine. So this is going to be the sine of u, which is going to be the sine of e to the x, evaluated from negative 1 to 0. Okay, so then this is going to be the sine of e to the 0, which is just sine of 1, minus sine of e to the negative 1, which comes out to be about 0.482. So this stuff is not particularly difficult. You just got to kind of make sure that you're not making careless mistakes. Okay, here you go. Here's your assignment. There's quite a few problems on there, but a lot of these go pretty quickly. And read the next lesson by next class. And I will talk with you guys later.